So today my talk will be about leveraging life-scale models for efficient learning, or in a much more simple word, distillation. So what are we talking about today? Well, we are facing the really dreadful and existential question, how can you improve a large language model? Well, there are not that many ways, actually. First one, you can increase the number of parameters. Indeed, the bigger, the better. You have more parameters and more computations, and you can make much better language model. That's for this reason, for example, that Llama created a 400 billion parameters model, which is great, isn't it? Then, you can improve the training dataset. By that, you can say, get more data. Well, we have an issue here because we have basically scraped the entire internet to create datasets, and it's not only true for Google, Gemini, Gemma, it's also true for OpenAI and most of our competitors. So we can not easily get more data. Okay, no problem. Maybe we can get higher quality data, like taking out the repetition, the garbage, or generated content. It's a lot of work, but at some point you also hit a wall here. Final possibility, you improve the architecture. Change a few layers here and there, add a few calculations, improve your optimizer, and so on and so on. But there, like, you can improve your architecture for years, and at some point you will also hit a wall. Like, you cannot get that much improvement from architecture. Of course you will, but you won't have a revolution for architecture alone right now. So what can you do once you have got the biggest model you could get? Like for Gemma, you won't release you a 100 billion parameters model because we want you to be able to run the model without needing a data center. We have scrapped the entire internet, and we have iterated on the architecture until we get the best one possible. Well, there is one final option, get higher quality data. And this is where distillation comes. So to understand distillation first, you need to understand how you train a language model. All language models, whether it's Gemini, Gemma, OpenAI, or anyone, are trained to do a really simple task. Predict the next word. So it's a bit of a simplification, but for the sake of this presentation, let's go simple. So they all do the same task. They predict the next word. What do I mean by that? Well, you have a sequence of words. For example, in here, the dog is, and the model will try to predict the next one, which will appear in the text. To do so, it will predict a probability distribution on its entire vocabulary. So if you remember Alex's presentation earlier, the vocabulary is given by the tokenizer, and we are talking about 200 of thousands of tokens of possible words. So in this case, the dog can be small, it can be blue, kind of unlikely, it can be brown, white, can be tree, because tree is a token in the vocabulary too. It could also be a Chinese character, a number, it could be many things. And on this, the model will give a probability distribution. So the dog has 10% of chance to be blue, 1% of chance to be blue, 10% to be small, 2% to be brown, and so on. But on the task, we know that the dog is actually brown. So what is the model going to do? Well, it's going to adjust its probability distribution so that brown probabilities will go a bit closer to 1, and all the other ones are getting closer to 0. And that's as simple as that. Okay, but how can you do better? Well, truth is not the best solution here. You can do much better than the actual truth. Let me give you an example. If I tell you my favorite animal is, well, 50% of you might tell me a cat. 30% of weirdos might tell me a dog. And the 20% left, yes, I love cats. The 20% left will tell me a bunch of random things. I don't know, snake, koala, orangutan, anything. But if in my text I have cat, well, my model will see, oh, for this step, cat is for 100% sure the best answer, and all the other ones are 0. This is not the truth. The truth is 50% for cat, 30% for dog, and a bunch of stuff for everything else. So how do you do that? Well, you take what we call a teacher model. A teacher model is a bigger model, a better model, a stronger model, which tries to train on a large data set, which gives great performance, and we can predict an accurate probability distribution, and insist on the fact that your teacher model must be good. If it's not going to work. So you give your teacher model your sequence of words, and your teacher model outputs you a probability distribution for the next word. And this is this probability distribution you're trying to match. So, in this case, we don't want brown to be at 1 and all the other one to be at 0. Brown should actually be at 0.5. Small should be at 0.1. So, it's already 0.1, so we are not interested. Blue, maybe there are some blue dye, 1% is fine, and so on and so on. So, if I sum it up a little bit, standard training, you have your input text. Actually, you put it through a tokenizer. Why? Because language model actually works with numbers. You have a sequence of tokens, and you try to predict the next token with a target probability, 1 for the answer and 0 for everything else. This is standard training. Distillation is a little bit different. You take your teacher model, and you run it through the input text, and you run it through your entire training data set. You get a probability distribution for each target, and this is what you're going to match. But does it work? This is a real question. And actually, I can tell you it does, 100%. Training is much faster. You need less time and less data to get the same results, which is pretty good, because as you may know, training a language model is insanely expensive. So if you can use less data, less training, it's always better. You have better performances, like your evaluation got better, but you have some downfall. First of all, you need a teacher model, and a good one. If you don't have a good teacher model, you're screwed. And most importantly, your student model cannot be better than your teacher. You're limited to the capacity of your teacher. So it's really interesting. For example, you have a really good 100B model. You are limited to 27B or to 10B. You're like, OK, I can do my best with that. But if your best model overhand is a 10B, you're not going to train a 27B on that. It doesn't make any sense. Another issue is the teacher can leak in some way to the student. Suppose that you are super good 100B model, but you were like, I wanted to be that really good on maths, and accidentally, whoops, I overfitted on the test dataset of math. Well, your teacher will also your student will also overfit. So you need to be really careful about that. And so some example. So here are some impacts. So we took a 2 billion parameters model and train it with and without distillation on several evaluation tasks that you can see here, on reasoning, code, or I think and common sense. And in each cases, you get an improve of performance. Thank you very much for listening to me.